is Venkat Subramaniam. I'm going to talk about laziness and tie this back into how we can actually benefit from the true value behind functional programming. So let's talk about laziness to begin with. So what does it really mean by being lazy? Well, being lazy simply means that, well, in a case of an eager evaluation, we execute a particular computation or a function or an expression as soon as we get hold of that particular expression. But rather than doing that, we're going to postpone it until A, we can do it later, or until the point when we no longer need the execution and we can just avoid it. So one of the benefits of being lazy is we can be more efficient by postponing computations. So one of the things I've learned over the years is, both in life and in programming, it really is valuable to be lazy. So we want to postpone things until the point where we can no longer postpone it. Well, let's talk about this a little bit. When it comes to programming languages, there are two ways in which we can execute code. And one of them is applicative order, and the other is the so-called normal order. Well, it turns out the normal order is actually abnormal. We don't use it too often. Most of the languages actually use what's called applicative order. Let's understand what that means with a little example to see how this actually works. So I'm going to start with an example in Java, but I'll show you a little bit of example in Haskell, just a little bit in Scala, and then we'll switch back to Java after that and look at a few more details. So let's talk about this applicative versus normal order. Well, it turns out most languages that we use in the mainstream use the applicative order. And so here is a quick little example to think about. Let's say for a minute we have a function to start with, and this function is going to be, let's call it compute. This is not going to do a whole lot right now. All this is going to do is simply return the given number, let's say. But I'm going to go ahead and print out, in this case, compute called, and so we can display the fact that this particular function was actually called in this case. But what I'm going to do here is, I'm going to define a variable x equal to 4, and I'm going to say if x is greater than 5 and, let's say, compute of x is greater than, let's say, 5 also, then I'm going to go ahead and say something called result, a little silly example. Otherwise, I'm going to output, in this case, let's simply say a no result. Well, here's a little example. So x is 4, if x is greater than 5, and if compute x is greater than 5, then I say result, otherwise I say no result. Well, a trivial question, of course. I'm going to run this code, but the question to you is, will the compute function be called or not? No, of course not. Why is that? 2 words. No, that's more than 2 words. 2 words. Short circuiting, absolutely. We all know short circuiting, right? So we have come to agree that, well, compute won't be called because of short circuiting. All right, so absolutely, that's exactly correct. So when I run the code, you can see that compute was not actually called, it said no result. Well, I'm going to do this a little differently. I'm going to go here and say int temp equals compute in this case, and then of course pass the x to it, and I'm going to put this as temp. Let me ask you this question. Do you want the compute to be called right now? No. Do you think compute will be called right now? How sad, isn't it? Well, don't you think that compute should not be called? Yes, you said you don't want it to be called, but it's kind of unfair, isn't it? Why in the world does compute get actually called in this case? Well, that's because by default, languages like Java do eager evaluations. So in other words, the language says, look, you called compute, I'm going to go ahead and call it. Well, wait a minute. Why didn't it then call it previously? Why was it okay to remove that in the short circuiting? It all comes down to one single thing. That's language specification. Languages have some specifications. They write down and say, that's what we do. Don't ask a question about it. In fact, it's kind of funny because when you read the C++ language spec, it's very glaring. The C++ language spec really clearly says, even if the constructor were to produce a side effect, the constructor may not be called, period. So languages make these clauses available, whereas mostly languages like Java, C++, C#, these are all imperative and object-oriented languages, so we do allow immutability of code. In other words, functions often have side effects. So unless specifically documented, the languages fear there will be side effect, and they eagerly evaluate these things. Let's step back and come back to this a little bit later. Let's go over here to yet another example. So here I am in Haskell. So I'm going to say in Haskell, and I'm going to say AB equals A plus B. And I'm going to go ahead and say evaluate in this case. And the evaluate takes a value and returns a value. Then I say main equals, in this case, of course. And what do I want to do in this particular example? Well, in here, I'm going to say print, and I'm going to call evaluate, and then I'm going to call add 1 and 2. Well, a very small little example, as you can see, and it, of course, produced the value of 3, which is, of course, 1 plus 2. But the question is, did add get called in this case? Well, we can kind of say, of course it did, because we got a total of 1 and 2, so there is no doubt about it. But how do you prove it? Well, in the case of Java, I put a little print statement to prove it. Sorry, I can't do that in Haskell. Because in Haskell, it is a complete opposite of languages like Java. In language like Java, the default is mutability. And you have to plead with the language and say, please, just this once, make this immutable. Languages like Haskell has what are called safe defaults. Languages like Haskell say everything is pure by default. If you want to make something impure, you have to make a special request. So I can just throw in print statements anywhere I want to and walk away. I won't be able to do that. Well, so how do I prove this? I never thought I would prove it by using a debugger. So I'm going to say GHCI, which is the interactive shell. I'm going to go ahead and load, in this case, sample.hs. And I'm going to put a breakpoint right now on line number 1. And I'm going to put the breakpoint in character number, let's say about 16 over here. So I'm going to say 1 and 16. Then I'm going to call main. And clearly you notice it is waiting for us in the add function. And I'm going to say continue right now. And it says 3. That's a proof that the code did execute the add function. We'll come back to that in just a minute. But I'm going to go back to this code. And I'm going to go ahead and change this to evaluate value. And I'm going to return a 42. Now, of course, when I run this code, you can see the result is 42. But the question is add being evaluated or not? Well, here's how Haskell works. You go to Haskell and say, hey, Haskell, call add. It says, why? Because I want to pass it to evaluate. But why? Because I want to pass the result to print. But why? Because I want the user to see the result. Oh, then just call print. Well, you call print, and it goes in there and says, gosh, I need the result of evaluate. Okay, then go call evaluate. And evaluate says, return a 42. Well, I'm done. Hey, what about add? Well, what about it? It's of no consequence, no use. It is absolutely lazy. How do you prove? Once again, let's go back to the GHCI. Let's go ahead and load up this particular code. Let's put a breakpoint right there in 1 and 16. Let's go ahead and call the main function. And notice it produced the result 42. It never hit the breakpoint. So that shows us that this actually never called. Well, this is called normal order. So normal order is different from applicative order. Well, change the word applicative to invocation or call, meaning the order in which a function is evaluated is the order in which it is applied, called, invoked. That is the default behavior in a lot of languages. Normal order is it wouldn't call the method when you apply it, but instead it will wait until that method actually becomes relevant. And if that method is not relevant at all, it would completely bypass calling that method. And so this is basically how Haskell works. Now, how is it that Haskell is able to do that? Well, the reason Haskell is able to do that is methods by default are pure functions. Functions by default are pure functions. Functions don't have side effect in Haskell unless, of course, you specifically mark them with what is called I/O. Well, I/O is not input-output. I say I/O stands for impure operation. So you are saying, I'm marking this, I'm coloring this function to say something funny, something smelly happens here. Don't optimize this code and evaluate it in the sequence in which it is being presented. Whereas a lot of other functions are pure, so they can be executed at will or not executed at all if it's not relevant. Well, that's awesome that some languages can do this. So normal is actually quite uncommon, like I talk about. But some languages are born lazy. I mean, when they were born, they were at the beach sitting and having nice drink, and they were absolutely lazy from the birth, whereas other languages have to work really hard to be lazy. Those languages are kind of like me. I'm always like looking for something to do, and my wife will say, why don't you just sit down and relax? I'm like, how do you do that, right? So the point is, we're always active, not very lazy. Some languages are like that. So we saw the difference between eager and lazy evaluation, but I want to go a little step further with this. How could we really make use of laziness a little bit further? So I want to entertain this thought a little bit further in Scala for a minute. So in the case of Scala, I'm going to define a function called compute, where I'm going to say, value, let's say, or number, and then I say number is a int, and I'm going to go ahead and say, in this case, equals, and I'll simply say compute like we did a few minutes ago over there on the other side. So I'm going to call the compute method, and I'm going to simply return the number, right? In this case, of course, I'm going to say x is equal to 4, and I'll say if x is greater than 4 and compute of, let's say, x is greater than 5, then I want to, of course, print out, let's say, result. Otherwise, I'll say else, no result, much like what I did, that silly code in the Java side. When I run this code, of course, what you notice in this case is that it is not going to go ahead. Oh, did I say console? Sorry, too much JavaScript going on. So let's go ahead and say print line, of course. So in this case, you can notice that I'm going to go ahead and call this method. Well, obviously, in this case, it will not execute the compute function because of short circuiting, as we know earlier in our examples we talked about. But on the other hand, though, well, it does say no result right here. Ignore the cat release. I'm messing with something else in this case. But you can see it says no result. It never called compute. On the other hand, I'm going to go ahead and take this code right here, and I'm going to call it as temp, as you would see. And then I'm going to go back here and say val, and then, of course, temp is equal to, and I'm going to provide that. Now the code is almost exactly like what we saw in the case of Java, with only minor syntactical differences, if you will. Well, obviously, in the case of Java, the code was eagerly evaluated, as you saw a few minutes ago. But the question is, what about Scala? Well, in this case, of course, we said temp is equal to compute and said, Scala, go ahead and run this. Well, x is, of course, not greater than 4. So when I run this, what do you expect? Well, sadly, Scala does execute the compute method, as you can see. Now, why is that? Well, the reason is, again, Scala says, I don't have a way to guarantee that functions are pure, so I can't just skip running functions after all, so I'm going to go ahead and eagerly evaluate it. So what it really comes down to is the purity of functions. If either you can guarantee the purity of a function, or if the language requires purity of functions, then there can be lazy about evaluating it. If the language cannot require purity of function and you don't guarantee purity of functions, then it's got to be eagerly evaluating it, unfortunately. But there is always that thing called language spec. So this code, as you can see in Scala, simply ran compute and printed no result, except you can mark this particular variable with this beautiful keyword called lazy. Now you are playing a part. The language spec says if you mark a variable as lazy, you are giving a bona fide certificate to the language to say, skip evaluating this until you can no longer skip evaluating it until it's required, or just forget it, don't even execute it. So now notice when I run this code, you can see that compute was never called because we marked this variable as lazy. And because you said it's lazy, the language says, I don't have to run compute. I will wait until you actually use it. On the other hand, if you notice, if I make the variable x 14, you can see that compute was actually called, even though we had marked it lazy. That's because, of course, now that x is greater than 14, temp is required, and temp is actually called. Just to make the point clearer, I'm going to say here but notice that compute is being called actually after the line that hits the here in this case. So again, print line, and you can see that compute is being called after the code hits the print line and not before. So you can see that was very lazy in evaluating the temp, as you can see. So in other words, languages can decide to be postponing evaluations until a later time. How does this really relate back to what we're going to do in languages like Java? Well, obviously the question is, does Java have a lazy keyword? Well, it doesn't. So language like C# give you a class called lazy, but Java quite doesn't. You can create one yourself if you're interested, but I'm going to move forward and do something else. I really want to postpone evaluations, but how can I do it? Well, this is where lambda expressions come in really nicely. Well, how does lambda expressions actually make a difference? Well, remember, a lambda expression is an anonymous function. So you are getting on your hand a function, and you are holding on to a reference to a function when you create an anonymous function. Now imagine this anonymous function is like an apple. Well, I could take an apple, and let's say we have a good friend here, Les, and I give him an apple. So here you go. And what are you doing with the apple now? Okay, there you go. He just ate the apple. Thank you very much. He could certainly do it. Or he could have other options too. For a minute, you notice he deferred. Well, no juggling apples. But I could have given him the apple. He could have done three things. He could eat it right away, or he could just keep it right there, and then he could eat it a little later on, or he could also give it to somebody else, hoping he has not taken a bite out of it already. So those are the four different options he has. He can use it right away, he can use it later, he can give it to somebody else, or he could trash it. So essentially the point really is, those are the different options you get. So if you think of what we can do with objects, we can do the same thing with functions as well, and lambdas are these function objects, if you will. So let's take a look at how that's going to help in what we want to do. So I want to talk about laziness, but before we talk about laziness, let's entertain this thought about how this could potentially be lazy. Well, in the case of Java, they have what's called a supplier. So if you notice this particular example, you can see that temp was evaluated eagerly, which kind of sucks. But what I'm going to do instead is, I'm going to turn the temp from int to supplier of integer temp. And then, of course, I'm going to go ahead and do something a little different. Watch this one very carefully right now. I am going to just copy and paste this so you can actually see the way this code is evolving. So here is the temp right now, but I'm going to change it to supplier of integer. And of course, in this case, I'm going to take this part right here, and I'm going to do one little operation to it. But before I do that operation, I want to say probably the most profound statement ever that I have come across in our field is profound a statement is the following words by David Wheeler. There is not a single day that goes by when I don't think of those words and I don't appreciate his words, because I think this is the most fundamental thing we all benefit every single day, and that is in computer science, well, that's what he says, in computer science, almost any problem can be solved by introducing, right, by introducing, if I don't know how to type introducing, there we go. So introducing one more level of indirection. So almost, not all, but almost every problem in computer science can be solved by introducing one more level of indirection. This was the words of David Wheeler, and I think that is absolutely phenomenal, because this is what we do every single day when we program. We throw in another level of indirection. Notice what I'm going to do in this example. Here is the call to compute. Let's introduce a level of indirection, and there we go. We just did. So we introduced a level of indirection. Rather than calling compute right away, call a lambda, which in turn will call the compute. So that is the level of indirection we introduce. Then I can say temp.get over here, and then of course when I run the code this time, you can see that it did not call the compute method anymore because we passed the lambda, but the lambda was never actually evaluated until the lambda is actually needed, and in this example it was actually never needed at all. On the other hand, if I were to go back here and put 14 here, Well, clearly we would need to evaluate it at this time, and you can see the compute being called right now. So it postpones evaluation until the point when you can eliminate calling it completely or call it later on when it's needed. So we brought the Java code back to what Scala was able to do, not by using lazy like we did in Scala, but by using the supplier here in Java, and then moving that into a level of indirection and using, of course, the lambda expressions. So what I'm getting to is, while a lot of languages do not support laziness question, yes, please.
So what if you call temp.get multiple times?
Right.
Maybe it was returning the current time instead of
You bet you. So you would have to do a little bit more work. You would have to do a little bit more work in that case. So in this example, it would reevaluate the get. The lazy wouldn't, right? That's why Java doesn't support lazy, but you can use this as a building block to build even further. There are several people who have written about it. I also have a blog about it, how you can use a supplier to build your own lazy. You got to do a little bit extra work to create laziness in Java, but it's not too difficult to create one. So what you could do is you could create a class called lazy, kind of like what C# has done, and then you could say, when you call me, I will cache it the first time you call it, and I'll return the value after that. You can definitely build it. Suppliers don't do that by default, so really good question, absolutely. You don't get that for free in the case of Java. I wish we did, but not so, but we can easily build one, to your point. So in this case, of course, one of the beautiful things about this is you are getting laziness in languages for free, but in languages that don't give you laziness, but do support lambdas, you can go towards laziness by building using lambda expressions. So in other words, what I'm getting to is lambdas are pathway to laziness. And that is one of the really beautiful things is with lambdas you can achieve laziness that you won't be able to get. A lot of different tools and frameworks and libraries rely on this idea very, very important because lambdas give you the pathway to laziness. But please don't assume just because we're using lambda that we are actually lazy. The language or the library should actually make use of it. Not all languages and libraries do, but thankfully Java does. So Java says, I'm going to take advantage of laziness when you give me lambdas, and we'll see how that is so in just a few minutes. So let's take a look at one example of this. I'm going to take a problem and solve it using the traditional approach, and then I'm going to show you how we can solve that using the lambdas and functional style of programming. Then I'll bring out a concern with the program and see how laziness saves our day. So let's take a look at an example to begin with. I'm going to start with a list of numbers 1 to 10, and my problem says find the double of the first even number greater than, let's say, 3. So I want to find the double of the first even number that's greater than 3. Now in this case, I'll say result is equal to 0, and I'll output the result at this point. Then I'll say for int I equal to 0, or let's say element in numbers, and then I'll simply say if element is greater than, let's say element is greater than 3 and element mod 2 is equal to 0, then of course result is equal to element times 2, and I have to break out of this particular loop right here. Well, it tells us the result is 8, but unfortunately though, that's not entirely true. Because if you notice this code, there are times when the collection may be empty. The collection may not have any even numbers at all. The collection may not have any number greater than 3. In all those cases, the result should have been non-existent, but unfortunately the result is a 0, which is incorrect. So the problem, first of all, is this code is verbose. This code is noisy. This code requires imperative style. It uses mutability. You have to sit there and tell every single detail in this code. So a lot of negative. With all that negative, it's even worse. This code is actually wrong. But the beauty of this code is it is very familiar. You can pretty much grab anybody off the street who knows Java, show them the code, and they're not going to freak out when they look at it, right? It's common. It's very familiar. However, before we go further, we want to get rid of this ceremony. what are the things we want to remove? We want to remove the mutability. We want to remove the imperative nature. We want to write the code in a functional style. So how do I make this code into functional style? Well, I'm going to go back here and write this again, but this time I'm going to say numbers.stream. Well, stream is an internal iterator. An internal iterator, rather than using an external iterator as we saw here, then I'm going to say dot filter, and given an element is greater than 3, now I'm saying given all the elements, give me the elements that are greater than 3. And then of course I'm going to say dot, and in this case I'll do a map given an element in this case times 2, and then of course I'll say find first. I just want the first element, and then or else just give me a 0. Intentionally in this case I want a 0. If I don't put it, it'll give me an optional rather than giving the 0, giving the value itself. So in this case we got the same result as the other one. However, I'm going to make a small change to this code and then argue about some of the differences. 1, 2, 3, 5, 4, 6, 7. So keep in mind the sequence of numbers I have. 1, 2, 3, and then 5, and then 4, and then 6, 7, 8, 9, and 10. When I run the code again, both of them should produce the same result in this case, isn't it? So in this case, of course, I'm filtering, I forgot the even numbers, didn't I? So filter given a e mod 2 is equal to 0. So both are giving us exactly the same result as you can see in this case. Okay, great. So we have the code doing the same stuff, but wait a minute, are we really having issues at our hand? Let's talk about the advantages before we talk about more specifics. Look at the code in the top for a minute. That's an imperative style code. We are looping through and going through the values and telling everything every single step of the way. Well, the code in the bottom, on the other hand, is a single pass through. Given all the numbers, get me only numbers greater than 3, then get me only the even numbers, then get me the double of the values, but pick the first one and then return to me 0 if it doesn't have a value. But wait a minute, how much is the cost of executing the code in the top in terms of computations? Well, before we answer that question, let's go back and do this a little differently. Let's go ahead and say public static, and I'll say Boolean is greater than 3, in this case, let's say number, and then I'm going to say return number right now, and then similarly, I'm going to go ahead and put 2 more calls in here. Well, this one is going to be, again, a Boolean, but I'll call this one as is even, and then of course, in this case, I'll say mod 2 is equal to 0, whereas here, of course, it's going to be greater than 3, and then finally, of course, I'll change this one to say int, of course, I'll call it as double it, and this is going to return number times 2. Well, I'm going to use this code in just a minute, so I'll go up here and say, instead of e greater than 3, I'll say e greater than 3, the method call. Similarly, instead of checking this right here, I'll call is even and pass that. And finally, I'll go ahead and say double it and pass this as well. So I'm just changing the code to use those methods. Well, this gives us a little bit of a clarity on the computation itself. But remember, the code we have with us is going through a int 1, 2, 3, 5. So let's see how many computations this is going to perform when we give that series. Well, in this case, is 1 greater than 3? Well, the answer is no. Well, is 2 greater than 3? No. Is 3 greater than 3? No. Is 5 greater than 3? Well, it is. Is 5 even? No. Is 4 greater than 3? Is 4 even? And then double it. Well, that was 8 computations to do the work. So we can say that given this particular example, this code took 8 computations to do the work. Well, that's great, but what about the one in the bottom? Well, let's be very naive about it without thinking much. This is a collection of 10 values. We're asking if each of the value is greater than 3. Oh my gosh, that's 10 computations. Dead on arrival, isn't it? Because 8 computations there versus 10 over here. But to add insult to injury, this is going to be asking if the numbers are even. That's 7 more values being compared. 10 plus 7 is 17. Plus, of course, we're going to double the values left. That's 4 more values because there are 4 values which are even and greater than 3. And that becomes 17 plus 4, which is 21. So that's 21 computations compared to 8 computations. So 8 versus 21. Well, you're going to say, wow, that's about 3 times more work you're going to do. But notice how beautiful this code really is. And you're going to say, get out of here. We're not going to give you 3 times more price because it looks beautiful, because we want performance of this code. Well, that's a fair statement. So oftentimes, when you look at languages like Ruby, languages like JavaScript by default, or even Groovy, that's exactly what those languages do, is they do all that extra work. So for doing functional style, you are compromising on performance. It may not be a big deal if the collection is a small one, but let's go to this and see what's going to happen now. You go back to this code and you add more values to the end over here in this example. Well, the imperative code is still sitting there at 8 computations, while the functional code may have to do a lot more work now, and then you kind of wonder, is this really true that we want to really explore it? But thankfully, in a lot of different functional programming languages, and even though Java is not truly a functional programming language, even in Java, what I said so far is not actually true in this example. Well, why is that? And the reason is the streams in Java are quite capable and different. Well, what do streams do in Java that we don't see in a lot of other languages? What does stream do in Java that we see generally in functional programming languages? Well, there's one character of stream that I've only seen among my own children. They both are lazy to the bone. So they don't actually do the work when they're told to do. I'll share with you an experience that I've often noticed at my home or I know about. So my wonderful wife, and I have teenagers. Well, if you have teenagers, you know what I'm talking about. If you don't have teenagers, if you were a teenager at one point, you know what I'm talking about. Teenagers are lazy to the bone. So my wonderful wife will tell my son, she would say, turn off the TV. It's as if no words were spoken because nothing really happened. Then she would tell him, take the trash out. Nothing happens. Then she says, do your homework. Nothing happens. Then she says, I'm calling daddy, and everything happens. So the point really is, these are lazy evaluations. So when you go to the stream and say, hey, stream, go ahead and filter, it says, never mind. Filter again, some other day. Map, maybe. And then you say find first, and bam, it's done. I mean, they could have renamed find first as call daddy. That would just work fine, or call mommy, depending on the family. But the point really is the evaluation is postponed. So there are 2 kinds of methods available in these languages. These methods are called intermediate operations, and the intermediate operations are fused together. On the other hand, the one in the next line is called a terminal operation, and it's a terminal operation that triggers the evaluation of the intermediate operations and not otherwise. So to prove this point, let's go ahead and comment out the functional style code for a few minutes. Let's only keep the imperative code, but I'm going to go back in this case and say is greater than 3 plus number. But before I go, I want to emphasize these kinds of operations are pretty much really bad idea. You want the functions called within lambdas, or in other words, you want the lambdas to be pure. In other words, lambdas should not have any side effects. So don't do what I'm showing you here. I'm just doing it here to illustrate for illustration purpose, but in production code, we should never make these functions impure. The functions that you call within lambdas and the lambdas themselves have to be pure. That's very important. Well, now that we talked about that, let's go back and drop these things here. And I'm going to say is even right there. And I'm going to say double it. And now I'm going to go ahead and run the code. And notice the number of operations we performed. It is 8 operations. This is the imperative code again. 1, 2, 3, 4, 5, 6, 7, 8 operations later, we got the result. So that is the imperative code. But I will comment out the imperative code and uncomment the functional style code. But before I run, let's understand how this actually works. What it doesn't do is it doesn't take 1 through 10 in that sequence and then pick all the numbers greater than 3 and say, here you go, a list of all the numbers greater than 3. It doesn't do that. In other words, the lines that are highlighted do not work on the entire collection. Instead, what it does is, it takes the first element 1 and says, go ahead and run this 1 through, and the 1 says, okay, thank you for calling, and it says 1 is greater than 3. No, 1 is not greater than 3, so 1 will fall out right there. It takes 2 again and says, try it. 2 is not greater than 3, it runs out. Takes 3 next, 3 is not greater than 3. It takes 5 next, 5 is greater than 3. 5 is, however, not even, so 5 bails out through the second door. Then it takes 4, well, 4 is greater than 3, 4 is even. It performs a double of the 4, and the 4 arrives at find first, and find first says, oh, thanks. And as soon as find first says thanks, the rest of the code says, gosh, looks like we are done. There is no reason to touch any of the other variable values. So in this example, it will never evaluate 6 and later because it has obtained the value up through 4. There is absolutely no reason for it to evaluate 4 and later, and it's going to be very lazy about it. To prove that, of course, let's go back and run this code right now. And when you run it, you notice in this case, I'm going to call these methods now so we can do a comparison. So sample, in this case, is greater than 3. And then, of course, I'm going to say sample and then is even. And finally, I'm going to say sample, double it. But notice now when I run this code, it performs exactly the same number of operations as the other piece of code did. Exactly 8 computations, but more important, notice it never touched the value 6 or later. So you could go off and add more data to the end of that sequence, but you will be guaranteed it gets off as soon as it finds the answer. It is absolutely lazy. In fact, to really understand this laziness a little bit further, let's go explore something a little different here. I'm going to go ahead and remove all of these for a minute. And then I'm going to simply say output right here, done. And then, of course, when in this case, when I say done right here, and when I execute the code, you can see it performed all those operations, and then finally it said done. However, notice in this code, we performed all the intermediate functions and then the terminal function. But what if I am going to stop this code, but one shy of the very last line? So I removed the find first from the sequence of call. I did the filter, the map, but I did not do the find first. What does the code do? The code now behaves like some employees you know at work. They come to work in the morning, they look around and say, hey, where's the boss? And you say, oh, the boss is out sick today. Yes, I don't have to do any work then. Well, after all, if there's no terminal method, why waste the time and effort doing the work? So in this case, notice when I run the code, even though I have the filter and the map available here, all it did was do done. It did not actually do the actual work because the map and the filter were all just lazy methods. It didn't have a reason to actually evaluate that method, so it just completely ignores that and says, never mind, I don't have to do all that extra work because nobody actually cares. In a way, if you really think about it, it's like you and me, right? Your boss calls you on January the 15th and says, I want you to work on this project, and your report is due on April the 15th. So on January 15th, you got this new project. The report is due on April 15th, so you get out of the office and you start on it immediately, right? Of course not. You are going to start on it promptly on April the 14th if you're like me. In fact, if you know secretly that you're going to quit on April the 1st, why in the world would you work on this project anyways, right? But on the other hand, you know how some bosses are really boring. The boss says, this is the new project for you on January the 15th and says, your final report is due on April 15. That word final knows what's going to come later is going to suck. Because the boss says your final report is due on the 15th of April, but an interim report is due every Friday. That life sucks. You got to work something every week then because there's a report due every Friday. The moral of the story there is, if a function has a side effect, you cannot be lazy. If a function does not have a side effect, the only way people will know what your function did is by looking at the final result, because it never changes the world around it during its execution. So in other words, when you think about functional programming, when people say immutability is very important, to me, immutability is like vegetables. You don't convince children this is important by telling them, eat your vegetables, because who wants to? Immutability is like vegetables. So when we go to programmers and say, you need to do immutability, they're like, get out of here, we got other better things to do. But why do we care about immutability? Because if your code, if your function is immutable, if your lambdas are pure, then your execution can be postponed to a later time. You can attain referential transparency in your code. You can have memoization in your code. Without immutability, you cannot have any of those. So lazy evaluation cannot exist in the presence of mutability. In other words, lazy evaluation is going to exist only if you can guarantee immutability in your code. That's one of the reasons why immutability becomes so important. There are other reasons, of course, but these things cannot exist without having the possibility of immutability. That's one of the reasons why it's critical. So in other words, what we talked about right now is that we got some really good benefits at our hand. So what is it? We start with immutability, and what does immutability gives us? It gives us a referential transparency. Now, what does that referential transparency really mean? Referential transparency means that the value of a function can be replaced for that particular function or expression. Languages like Haskell do this phenomenally well. I was blown away by Haskell one day. I was working with Haskell. I made a call to a function. That function involved a lot of work, and it took a good 15 seconds to run. And at the end of the 15 seconds, plop, the result showed up. And I said, okay, that's great. But for whatever reason, I said, run it again. And when I ran it again, Haskell came back with the answer like, plop. I'm like, whoa, how in the world can you give me the result instantaneously when you just took 15 seconds to run? That's when I discovered what Haskell was up to. Haskell automatically can store things into a thunk and then reevaluate that value and give it to you rather than re-executing the entire function. But language is able to do that because there is a guaranteed purity. Well, when it comes to Java, Java does not guarantee purity when it comes to regular functions. Hey, what about lambda expressions? Does Java guarantee purity of lambdas? Java does not guarantee purity of lambdas, but I believe Java does something even better than guaranteeing. Java assumes that lambdas are pure. I love languages that assume like that, because if you and language are in disagreement, you know who wins, right? The language always wins. So the language says, you're on your own. If you're messing with stuff within lambdas, I will not warn you, I will not give you an error, and things will fail in unpredictable ways. So you and I have to guarantee that lambdas that we write and the functions we call from lambdas are actually pure. That's our responsibility in languages like this. But as you can see, immutability gives you referential transparency. Immutability gives you ability to do memoization, where you can store the value and then reuse the value any number of times by just returning the pre-computed value for the same input. That's because pure functions have the ability to give you the same output as long as the input is the same. But we also have the ability to perform laziness, and of course, there's another benefit of this, which is easy and safe parallelization. So in other words, we cannot have laziness without immutability, but the minute you bring immutability, you got all those benefits. But what about laziness? What's the benefit of doing that? Well, if you're lazy, you can be very efficient. So when you say the word lazy in Java, you pronounce it as efficient because you get efficiency from it more than anything else. But there is one other benefit of laziness that you get also that is a very charming feature, and that is infinite streams. And so you can see how one good thing leads to another good thing, and you are moving towards something much bigger and better and for a greater good. So infinite streams become available as well when you are able to move towards laziness. How so? Let's look at an example of how infinite streams can help. So what I can do in this case is, let's say I have a collection of values, and in this case, I'm going to go ahead and say, let's say write a function. And the function I want to write is the following. I'm going to say, call a function, let's say output, and I'll call compute with n and k. We'll come back to that in a minute to see what it means. So n is equal to 51, and let's say k is equal to, let's say, 142, or some random numbers. But what is compute going to do? Well, I'm going to say public, let's say static double compute, which takes an n and takes a k. Well, in this case, I'm going to say something along the lines of return the total of square root of all even numbers, let's say starting as all, not all, k even numbers, let's say starting from n. Well, I want to return the total of square root of k even numbers starting from n. How would you write this code in the imperative style? It's going to become a total mess very quickly, isn't it? Because you're going to say int index is equal to n, int count is equal to 0, and then you say, in this case, a double result. So you're going to say double result is equal to 0. And of course, you want to return the result when you're done with this whole computation. But then you're going to say, while, in this case, count is less than k, then you're going to say, in this case, you're going to increment the value, but you're going to say if index mod 2 is equal to 0, well, then you're going to say, well, result is plus equal to math dot square root of that index. But then we're not done. We got to increment the index. So you're going to say count plus plus to increment the count, index plus plus to increment the index. But look at this code, how complex it becomes very quickly. You got to increment the count inside the if. You got to increment the index outside. If you get it wrong, it's going to be wrong. And most likely I got it wrong already, right? Any problems? Yeah, you could use a for loop, but then how do you know how many to go? You got to keep skipping also, right? But the whole point is, whether you're using a for or a while, it is complex. And you're going to stop and think about it and say, is this correct? Is this what I should do? Is the boundaries correct? But the question is, why bother? We can do a lot better than any of those now that we know how we can use functional style. So we're going to use a lazy evaluation because we're going to create an infinite stream. So how do we go about creating an infinite stream to do this job? So 1922, it says, well, we don't know whether it's right or wrong, but nevertheless, let's try this. Return stream, where stream comes from the Java util stream package. So I say stream.iterate, starting with the n, given an element, element plus 1. Well, that gives you an infinite stream right off the bat. So we are starting with n plus 1, n plus 2, n plus 3, n plus 4. But the beauty is, this is lazy evaluation. It will not evaluate this lambda expression until you demand for its value. Then I can say, well, thanks, but I'm going to filter, and I'm going to say, given an element mod 2 is equal to 0, well, that becomes only the even numbers I'm interested in. Then I perform a map to double, and I'm asking for math square root, and I'm asking for the square root computation. Then I say limit to k, and then perform a sum operation on the result and return the result from it. Well, notice how we're not dealing with for loops or while loops or all the loops and the boundary conditions and all that stuff. Life becomes very easy thanks to lazy evaluation, which leads to the ability to write infinite streams. Well, we have not explored infinite streams as much in our programming with language like Java because mainly we never had those capabilities until this point, or at least not so easily expressive and fluent until this point. But this gives you that phenomenal benefit of making the code very highly expressive. Even if I used a for loop, even if I used a while loop, I'm going to look at the code and stare at it and say, how does this work going back and forth? This becomes a single pass through the code. Given all the values starting with n, only get me the even numbers, get me the square root of the even numbers, but only get me k of them and total it, and that becomes highly expressive. As you can see, you don't have to work that really very hard to get the code to produce a result you are interested in. And of course, we can't do this if you did not have laziness. So laziness leads to the greater good again. You got efficiency in code, but you also have infinite streams available to you also. Those are the benefits you get. If you're interested in downloading the code examples I showed you, you can download them from my website. I hope it was useful, and I hope you'll be eager about being lazy. Thank you.